Hey, welcome to Chapter 4. We're skipping 4.1 and going straight into section 4.2. All right, so through all of Chapter 3, we talked about functions and how wonderful functions are and all the great things that we can do with functions. 4.2, we hit a roadblock, acknowledging that in the real world, we usually aren't given functions, we're given data. Most jobs today are centered around trying to understand and process data. Uh, so companies nowadays are really good at collecting data and less good at analyzing what it actually means. My girlfriend works in business analytics for RSM Consulting, and basically her whole job is just to go to different companies and just tell them how to work with their data. So she'll go to companies and they'll tell her all these wonderful data sets they've collected, and they have no idea what to do with it. So it's her job to then figure out how to process that data and understand that data. So in this section and in the next section, section 4.4, we're going to talk about the very basics of data analytics, just to get everyone on the same page and to give you an introduction to the topic. So oftentimes, we want to pull a function out of data. And to do this, we can look at a relationship between variables. So you might be presented with a scatter plot. And the data might exhibit some sort of relationship. So you might find that the data looks something like this. And we're not quite sure what function would be best suited for this, but we might predict that this data is best modeled by and pause the video and fill in this blank. All right, and coming back, we would find that it's best modeled by a quadratic. And that's just guessing where it looks like we can just draw a quadratic into this data set, and that gives us a pretty good approximation of our data. And we're interested in these approximations because say our data was cut off here at x equals, let's call that 15. We want to know what to expect for x equals 18. Well, if we have this, once we find this quadratic fit, we can then look at the function for this quadratic and then just evaluate it at f of 18. So let's call this line f of x. Then, what the heck? Sorry, I don't know where that whole line went. Huh. All right, so we're trying to ask what happens for x equals 18. And so we take this function f of x, this quadratic that we found, and just evaluate f of 18. And then whatever that value is what we would probably expect f of 18 to be. And then maybe you could guess that this probably only works well for values around what our data is. We might not be able to get a good approximation for what happens when x is 100. So that leads into this next point, is that functions can be used to then predict the future. In particular, you might have a business with quarterly financials. And maybe they look something like this, where they had a couple good quarters, maybe a bad one, it picked up well, they declined for a little bit, started to go up, you get a bad quarter, but then you get back on footing and it looks like it's leveling off a little bit. Then you could either find the line of best fit, you could find a curve of best fit. This is actually where computer scientists have started making machine learning models to guess what's going to happen next based on what's happened in the past. So then find a function that fits. So maybe it's going to look something like, it's kind of increasing. And so it'll keep increasing as we go towards the end, but maybe it'll be safe and drop down a little bit, or keep picking back right up, because that's kind of what the shape of the data looks like. So this whole part is our guess of the future. We know everything that's happened up to this point, and so everything after is the future that we're uncertain about. And in the past, people have used these linear models. Nowadays, the big thing is probabilistic models, where you use some sort of statistics and probability to create a model that'll tell you a bunch of different outcomes with different percentages. But part of understanding those is first understanding how it works with just a function in this so-called deterministic case. And so we create this function, and it'll tell us that we probably expect it to be somewhere in this range. And part of this, it goes along with our intuition, where we would be shocked if it was down here. If we had really high profits and then had a huge decrease, we expect only a small decrease. And because recently it hasn't had a sharp increase, we're not expecting to get another sharp increase. So if it was all the way up here, that's also unexpected. Expected to be pretty close to what we've seen. And then one final thing to know about that we're not going to cover in this class, but it's important to know about, is principal component analysis. Data analysts in the profession and in research talk about this all the time. They love it. It's one of their favorite tools because it allows you to do something called dimensionality reduction. Essentially, your dimensionality is the number of variables collected. And so sometimes you end up with a huge dimensionality for your data set. Imagine you're trying to conduct an experiment from people, and you have all these variables about people. So in your experiment, you've collected their age, their gender, the state they live in, their income level, their profession, their education, and so much more. So you have at least a dimensionality of 6 in this case because there are 6 variables right there. Well, it turns out that when you're trying to study data, it's pretty rough when you have a lot of variables, particularly the amount of computations you need to do grows quite fast. So we might be interested in just 2 variables. So we want to pick out 2 variables that matter most. So maybe you're trying to figure out how lucky or how likely someone is. How likely someone is to run for political office. That's the question you want to answer. And you want to pick out 2 variables that determine it the most. And that might be, you could take a guess. And so pause the video and take a guess on which 2 variables affect it the most. Of course, there's no right answer, but just for the sake of the video. All right, so if I had to guess, I would say that you would look at profession and also education. I'm saying this because if someone's already in a career that's politically oriented, they're more likely to run for political office. It's unlikely to have someone who has just a high school degree or even a bachelor's degree run for political office. So education can be a big factor in it as well. So maybe you would look at just those 2 variables to make a prediction. Principal component analysis, though, creates combinations of variables. So it'll actually pick out a combination of a variable, such as something that would look like 0.5 profession plus 0.4 education plus 0.1 income, and call that something like the strongest variable. So this weighting gives us the variable that's most likely to determine if you're likely to run for political office, and then I could pick out another one as well. And then you just do your data analysis with those two kind of artificial variables. And so then you've reduced it down to just 2 variables. But in practice, if you're ever listening to a data analyst speak, and they say principal component analysis, the takeaway is that they're using a computer algorithm that's going to pick out a combination, 2 variables that are formed from these other variables that determine the data set the most. So it might weight some things very low, such as state probably doesn't play that much of an impact in it, so state might not show up, and then we could kind of get rid of it and just forget about it. All right. And so what we're interested in doing for this class is actually finding the line of best fit. So suppose you're given a data set, we could plot it in this sort of scatter plot. And for this example, I decided to do height compared to age, age for 0 to 18, and height on the y-axis. And the first temptation to find the line of best fit would be to just pick 2 data points and create a line for it, and create a line that looks like it's going to go through the data set. So you might say this point and this point look like good points to choose, and you create the line through it. And it looks like that, which approximates your data set pretty well. This is all good, especially when you have a human doing it, so they can choose a line that looks like it'll fit the data set well to approximate the line of best fit. This unfortunately doesn't work well for computers, because computers, if you've ever done any programming, are stupid. If you tell them to just pick 2 points to make a line of best fit, they'll just pick 2 points randomly. So they might pick this one, and then say that this line best approximates our data set. To which I would say, no, it doesn't. It's not even close for most points. So we need to do something a little more clever. And so what we're going to do is first change the color of this pen, and then find averages. So if we have multiple points collected for each age, we can just average those points. So then we would find that we have points along here. And since they're all averaged, they're all pretty close to the center of the line of best fit. And then we can just pick 2 points again and just draw the line through them. So that works, where we just take 2 points, 2 of our averaged points, and make the line through that. So pick 2 averaged points and create line. To find the actual line of best fit, it's not that hard, but it's beyond what we can do at the college algebra level. You need just a little bit of calculus. So actually, I think after Calc 1, you could solve it. And we will use Excel and Desmos to solve it as well. Computers can do it pretty quickly. But for us, we're also happy with just approximating the line of best fit by just finding average points and creating a line. All right, I hope you enjoyed this video.